Good evening, participants. We are sorry that as we are running a little late, so we are forced to start the last session for today with a very short break. So I request all the participants to kindly join at the earliest because we are having our next resource person already ready with her exciting presentation. So just as an intro, I would like to say that statistics, it's not only important for our machine learning or for artificial intelligence, for any kind of discovery, be it in the domain of arts or engineering or science or technology, whether this is affecting the well-being of mankind, whether it is required for society or not, that has to be decided by the statistical significant measures. And that's why whenever we are talking about the cutting edge technologies in AI, in machine learning, or in the era of model predictive control, what we cannot go without is the statistics. So statistics is entangled with every component of our study. And when Anuradha and I were planning for this FDP, we were very much sure that we should bring into light that how statistics is required or how statistics has influenced AI and machine learning. So with this concept, we are fortunate enough to have three resource people in this FDP. Today we are having one of them, Dr. Prabhrisha Rokit, with us, who will be highlighting us with the contribution of statistics at the very primitive era of machine learning, that is regression analysis. So just as a formality, I'd like to introduce Dr. Rakshit with all of you. Uh, she is currently second year postdoctoral researcher at University of Pennsylvania, USA. After completing her BSc in Statistics from St. Xavier's College, Kolkata, she pursued MSc in Statistics from Indian Institute of Technology, Kanpur, acquiring first class first. She started her PhD in statistics in Rutgers University in New Jersey, USA in 2018 and defended last year only in May 2023. Her thesis revolves around high dimensional regression and its applications. Finally, she was offered postdoctoral researcher position in UPenn, where she has been working since July 2023. Her work mainly concerns causal inference techniques dealing with health-related data, and her research interest includes uncertainty quantification and prediction, variable selection, non-parametric inference, and causal inference, just to name a few. So without any further discussion, her work will say what she is. I request Dr. Rakshit to start her presentation and handing over the session to you. Please, Dr. Rakshit, it's all over to you now.
Thank you. Thank you so much for the kind introduction. Let's get started. And good evening, everyone. I was gonna say good morning because it's morning in the US, but yeah, good evening, everyone. I can be sounding like a misfit in the group of all engineering people, but as Pratyusha Rakshitji kindly mentioned that statistics, everybody nowadays is hyped out about machine learning, and there's a bit of a misconception is machine learning is all about mainly computer science engineering techniques, but and there's also this argument going on whether statistics is more about machine learning. Is machine learning just a fancy name for statistics and regression, or is it really like just a thing about the computer science people? But recently, people are understanding it's not a debate. It's basically the amalgamation of both the fields. Computer science people, the engineering people, basically give us algorithms, and we do the analysis. So it's a hand-in-hand situation, and hopefully, I'll be able to give you an insight about the statistical part. So let's get started with the presentation today, with the talk today. So As the title suggests, we are going to talk about prediction in high dimensional regression. But first, let's talk about what is regression analysis. So we will start from the very basic level and then introduce the more complicated and advanced techniques. So regression is a powerful tool in data analysis, which is widely used in real world applications like predicting house prices based on location and size. You might want to forecast sales based on advertising budgets, or you might want to estimate health risks from factors like age, cholesterol levels. So, why do we choose regression for that thing? First, it allows us to model relationships between variables, which means we can quantify how one variable influences another. In some sense, it helps us identify key predictors and uncover the hidden patterns in the data. And at its core, regression provides with two key benefits. It gives us insights into the structure of the data and enables us to make predictions that inform decision making. So that's the thing which kind of sets regression apart from many machine learning algorithms, because decision making is very unique to regression analysis. Not all kind of algorithms can do this. So whether you are predicting a future outcome or understanding underlying relationships, regression is a really powerful tool to have in your back pocket. So at its core, linear regression models the relationship between a dependent variable and one or more independent variables. So here we assume we have a sample of size n, meaning there are n observations in our data. Now for each unit in the sample, the model for linear regression can be written as yi equals to beta naught plus xi1 times beta 1 plus some xi2 times beta 2 plus so on and so forth till xip times beta p plus epsilon I. So what are all these symbols? Let me explain. So yi here is the dependent variable for the ith unit. xi1, for example, it represents the first predictor for the ith unit. xi2 is the value of the second predictor for the ith unit, and so on and so forth till xip you can explain. Now these betas like beta naught, beta 1, beta 2, these are all just the coefficients which we call the regression coefficients. These are unknown and we want to know about them because they are going to tell us about the relationship between the dependent or the independent variables. And then epsilon I, this is basically the error term for the ith unit. So that's basically capturing the variation which is not explained by this linear relationship, which is not explained by these predictors here. Now, if we collect all of these equations across the n observations and basically stack them one upon the other, then we can represent them in a more compact matrix form. So what we get from rearranging these equations is basically y equals to x beta plus epsilon. Here, y is basically an n-dimensional vector of dependent variable values. X is basically the matrix of independent variables, and the dimension of X is basically n cross p plus 1. Why p plus 1? Because p many covariates here, x1, x2 to xp, and then one additional one taking care of the intercept here. Basically here there's an x0 you can imagine, and the value of x0 is basically 1 for every unit. And then comes beta, which is again a p plus 1 dimensional vector. Why p plus 1? Because again, from beta 1 to beta p, and then in the front there is also one beta naught. So p plus 1. And then epsilon is an n-dimensional vector of the error terms. One important thing to understand is that when we say linear regression, so the term linear refers to the parameters and not the variables themselves. So the relationship between the dependent and the independent variables is supposed to be linear in terms of the parameters, not the variables. So it is just a convention how linear regression is defined, and there's nothing to do with any particular reason why it's defined in terms of the parameters, not the variables. But you just need to keep this in mind. For why? Because, for example, if you have a different model where you have yi equals to beta naught and there's only one predictor, maybe x1. So maybe you express it as yi equals to beta naught plus xi1 beta 1 plus maybe xi1 square beta 2. It is still a linear regression because your relationship is still linear in terms of the parameters beta naught, beta 1 and beta 2. It doesn't matter if the predictors are entering in the equation in a linear form or not. For example, xi1 square, it's not a linear function anymore, right? But doesn't matter. You can still apply any techniques of linear regression even now, just because the relationship is linear in the parameters. Just wanted to make clear about this misconception that many people have. So any kind of polynomial equation will also fit in the structure for linear regression. Now, a powerful part of linear regression is that it not just helps to estimate the relationship, but under certain assumptions that we are going to discuss, it also allows us to interpret them. For example, if you take this equation here for the ith unit, and you keep all of this beta naught, beta 2 and beta p constants, and then you basically take a partial derivative on both the sides with respect to beta 1, what will you get? You will get basically the partial derivative of y with respect to beta 1 is equals to is just xi1, right? So basically the beta 1 is kind of telling you how x1 is affecting your response variable when you are keeping everything else fixed. So that's a very nice interpretation, right? Now, next natural question is, if these betas are going to tell me all about the relationship and it's also helping me to interpret the relationship, but we don't know what these betas are, right? Because these are unknown parameters. We know that there are some beta that are going to tell us everything we want to know, but we don't know what these betas are. And obviously, because we do not know the truth, what we do is we try to make the best guess based on the sample that we have. So we have a sample of size n, and we want to guess, or in other words, in statistical terms, we said we want to estimate the value of these beta coefficients based on our sample. So how do we do that? So to understand that, let's start with a very simple example where we have only one dependent and one independent variable. Say we have a sample of observations on mileage and weight of 32 cars, and we want to find the relationship between these two variables. So I don't want to just impose or throw it on you that out of no reason we want to study the relationship between two variables. I first want to motivate why this could be a practical problem. Why do we want to find a relationship between like a fuel efficiency or the mileage and weight of the cars? Now, there could be multiple number of reasons. First, it could be that we want to predict the fuel efficiency of cars with different weights, because that will help consumers make more informed decisions about what car he or she wants to buy. It can also help in cost benefit analysis for vehicle manufacturers, because it can guide them on how much weight reduction would be needed to achieve better fuel efficiency. It can also help to maybe design an environmental policy, because lighter cars typically consume less fuel, which leads to lower carbon emissions. So in short, multiple reasons could be there why you would want to learn a relationship between fuel efficiency and weight of cars. So how do we start the analysis? First thing first, we have a data, we just plot them. This is something we call a scatter plot. So we have weight on the x-axis, and on the y-axis we have the miles per gallon, the mileage or the fuel efficiency of the cars, and we have plotted the data just so that we can visualize it. Now, what do we want to do? We want to fit a straight line through this data. And the straight line should be as close as possible to all the data points that we have. So that's like finding the best straight line. Best in the sense that it best fits the data, which in turn means that the straight line is as close as possible to all the data points collectively. Now, how do we do that? First, think of an arbitrary line through the data. Let me say that this blue line is just an arbitrary line that I have thought through the data. Now, if we take a particular value of the weight, let's say I am considering this weight value here, then there will be an observed mileage here. Now, this observed mileage value will in turn have a predicted mileage value that lies on this arbitrary straight line that you have imagined. Then the vertical distance between this observed mileage and the predicted mileage is what we call a residual or an estimated error. Now, these residuals measure how well the model fits the data. In this case, the model is just a straight line, right? So residuals are telling you how good or bad the straight line is fitting your data. Because smaller the residuals means a better fit. So the concept of least squares, there's so many methodology to find the best straight line going through your data. And the most popular one is called the ordinary least squares. It was introduced back in the 1800s by a very popular mathematician called Gauss. And you will be fascinated to know how simple and intuitive the idea is, yet so powerful. So what does least squares says here? How to find the best straight line? Least squares works by finding the value of beta that minimize the sum of the square of these residuals. So what does it mean? So you take all of these red vertical distances and then you square them and then you sum over them. And then you try to find the betas that will minimize this kind of a loss function. So this minimization will ensure that the straight line that you are trying to kind of estimate is as close as possible to all the data points collectively. Now, why do we square these residuals? We could have said that all we want is to minimize the distance of the points from the straight line. So why don't I take the raw residuals as it is, sum over them and minimize them? But what could be an issue in case you just look at the residuals and do not square them or don't take any other function of it is, for example, this one here is a big error, right? But this one is also a big error. But if you just simply sum over the residuals, this one and this one can get cancelled because they are in the opposite direction. So collectively, it will give you an illusion that overall the error is small, whereas individual error will still have big magnitude of error. So we square the residuals so that it makes sure that the positive and the negative errors do not cancel each other out. And also squaring the residual ensures that we are penalizing this large kind of errors more heavily. But you could always minimize some other reasonable function of the residuals also. For example, maybe not square them, but take an absolute value here. So for example, you can sum of the absolute value of the residuals and then minimize over them to get the best beta. Why don't we do that? In fact, this kind of regression technique also has a name. When you take the absolute value of the residuals, sum over them and minimize them. This is something we call least absolute deviation or LAD regression. That was actually, in fact, introduced way before least squares came into being. But as soon as least squares was introduced, it took over LAD regression. One reason is, of course, the computational ease, because least squares problem can be analytically solved to have a closed form solution. Whereas if you take just the absolute value, so what happens is like everyone knows that the mod function is not smooth function. It's not a smooth function. It has a kink at the origin, right? So what happens is that you can't really analytically solve that particular minimization problem when you do LAD regression. And that was one main reason why least squares became more popular than LAD regression, because it has a closed form solution, right? And one more interesting part that why least squares is so popular is the simple geometric interpretation that follows for least squares. So if any of you are acquainted with the concept of projection, then you would know that geometrically, least squares is nothing but just a projection. We are projecting the vector of observed values, y, onto the subspace that is defined by the independent variable x. So to understand what I just said, let's take an even more simple example. So basically we have a data on three variables and we have three observations for each variable. So the first is basically the variable y, which is the dependent variable. And then we have the variable x, which is the independent variable. And then we have a constant vector here, which is basically just taking care of beta naught, the intercept, the constant part of the equation. Now consider the first column as the vector y, this column. Now what is this vector giving us? This vector essentially gives us the coordinates of a point in the three-dimensional space, right? It is giving a point whose first coordinate is 2, the second coordinate is 3, and the third coordinate is again 2. Similarly, I will have two more vectors, one for this x and one for this c. All of these three vectors are in the same three-dimensional space. Now, this gray shaded region is basically just the space which is spanned by the vectors x and c. But clearly, this vector y lies off this plane. So the goal here is to find a vector that is in this gray shaded region and is as close to our vector y as possible. And how do we get that kind of a vector? We know from the theory of projection that the best vector is the orthogonal projection from this vector y to this gray shaded region. And let's call that projection y hat. So because now y hat actually belongs to the gray shaded region, and if you can recall what this gray shaded region was, this was basically the space spanned by x and c. So now because by construction y hat belongs to this space spanned by x and c, you can say that y hat can be written as a linear combination of x and c. Precisely, y hat equals to some beta 1 times x plus some beta naught times c. Now what I'm saying that these scalar coefficients beta 1 and beta naught are just the coefficients that we derive from least squares. Why? Because we know that the orthogonal projection of y onto this space minimizes the error between our observed y and this projected y. And this is the same as the minimization problem that least square solves, as we just outlined in the previous slide. So this geometric interpretation is one of the most beautiful things that least squares have and none of the other regression techniques have. And it gives us further insight as well. For example, it says that the total variability in y can be decomposed into two orthogonal parts. The variability that is in the direction of the column space of x and c, or that is the variability explained by our model, and then a variability which is in the direction orthogonal to this column space, which is basically the variability which is not explained by our model. Now let's come back to the simple example, the car example that we were looking at. So in this graph here, the red solid line basically represents the mean of y, or something that we denote by just y bar. So if you have like 32 y values, you take a mean or average of them, that will be a constant value, and that is shown by this red line here. Now these green dashed lines, they show the total variability that is captured by the total sum of squares, because this green basically these green points are showing you the deviations of these data points from the mean. Now if you basically aggregate all of these green deviations, square them and sum them, then you will get a total sum of squares. So it's kind of capturing the total variability that you have in your y values. And least squares regression allows us to decompose this variability into two parts: the explained variability and the unexplained variability. Now, this explained variability is captured by the sum of squares due to regression, which is basically what this yi hat is basically your predicted y. So that's the value that is corresponding to your observation, but lying on the straight line that you have fitted to your data. Y bar is the mean. So sum of squares due to regression is kind of giving you the variability that is explained by your data, because this is the deviation from the mean, but for your predicted value and no longer the observed value. And the other part is the sum of squares due to error, which is basically saying the part that is not explained by your predicted value. So the distance between your observed and the predicted value is reflected in the sum of squares due to error. And least squares is saying that the total sum of squares, that is the total variability, can be decomposed into exactly two parts, and there is no other cross product term, which is first part is due to the regression due to your model, and the other part which is due to the error part. So this naturally gives us a measure of goodness of fit, is what we call R square, which is basically just the sum of squares due to regression divided by the total sum of squares. So R squared is basically asking that how much better does the regression line perform than simply using the mean. So R squared gives us the proportion of the total variability in y that is explained by our regression model. So it ranges from 0 to 1, because as I mentioned, it's a proportion. So it ranges from 0 to 1, where 1 means that the model explains all the variability that is in your observations, and 0 means that the model explains none of the variance. So that kind of gives an idea how least squares work and why, in spite of being a very simple technique, it is so powerful. Now we are going more into the depth of the advanced techniques once we are done with the least squares. So one problem that you encounter in multiple regression, as in the sense of when you are working with multiple x's or multiple predictors, the issue that could arise is called multicollinearity. So multicollinearity happens when two or more of your predictor variables, so two or more of your x's, are highly correlated with each other. So in simple terms, these predictors are basically providing, so if two x's are highly correlated, so they are basically sending out very similar kind of information to the model, right? So that creates redundancy, which makes it hard for the model to figure out the true effect of each predictor. It cannot really distinguish between these highly correlated predictors, that it cannot really assign the contribution differentially to the two predictors. So basically the model gets confused. So the coefficients can become unstable, the whole thing becomes unstable, and our model will be giving us unreliable results. So to handle multicollinearity and other issues, we can have regularization techniques. So something where we basically add some kind of penalty to the usual loss function. For example, we let's look at a particular technique which we call the reach regression. So reach regression basically adds a penalty to this loss function. And how does the penalty look? It is basically just the sum of the squares of the regression coefficients. So how does that help to tackle the problem? Let's take a closer look at this graph on the right hand side. So here we are just considering two variables for simplicity. So basically we are saying that p equals to 2, so that you get to understand the simpler concept, and then you can try to visualize it for higher dimension. So In this particular graph, you are noticing two main features. The first is basically this elliptical contours, and then there is a circular region around the origin. So these elliptical contours basically represent the usual residual sum of squares, this one here, that we try to minimize in case of the least squares. And this point at the center represents the combination of coefficients, as in the combination of beta 1 and beta 2, that gives us the smallest residual sum of squares. Now, in ridge regression, we not only want to minimize this residual sum of squares, but we also add a penalty term. Now, for the two predictor case, that is when p equals to 2, this penalty term will look like beta 1 square plus beta 2 square. So that exactly corresponds to a circle with the origin at the center. So this circle basically represents the range of possible coefficient values under this particular penalty for the ridge regression. So the larger the value of this lambda, so lambda we call it a penalty parameter. So the larger the value of the lambda, the smaller the circle becomes, which in turn increases the penalty. But if we decrease the value of lambda, then the circle will be expanding more. That is, in other times, it is basically expanding the scope for the regression coefficients to grow a bit larger. Because ridge regression is saying that no, I'm not only gonna try to minimize this residual sum of squares, as in the case of the least squares, I'm also going to try to constrain so that the values of beta 1 and beta 2 remains within this circle. So how do we do these two things together? The optimal solution is found where this contour will be intersecting on this constraint region. So this, for example, here, this red contour is touching the constraint space, and that is where the optimal solution will lie. So ridge regression is basically trying to strike a balance between minimizing the residual sum of squares and controlling the size of the coefficients. So makes it very useful method for dealing with multicollinearity, because when you are controlling the size of the regression coefficients, in other words, you are saying that I'm not going to let the regression coefficients expand in an arbitrary manner, because when there's multicollinearity, there's so much noise in your model that everything is going everywhere. So your regression coefficients might just blow up in a very unpredictable way. So ridge regression, by applying this penalty, is controlling the size of those regression coefficients. It's not allowing it to expand or blow up. But you might ask, is something special about this particular form of the penalty? Yeah, obviously, and in the sense that for ridge regression, it is like a circle in the two-dimensional case, but in the high-dimensional case, it is basically a sphere. So just kind of a circular constraint space. But you can always replace it with a different kind of a penalty. For example, while ridge regression adds this circular kind of a constraint, another regularization technique exists called the lasso, which uses basically the sum of the absolute values as the penalty term. So mathematically, this means that in lasso, if you look at the contour plot again, that's the same contour plot. So we have again two regression coefficients, and we are trying to see how the residual sum of squares and this penalty parameter are interacting with each other. So you can say that everything almost remains the same except for the constraint space. The constraint space in the previous one, in case of ridge regression, because it was sum of squares of the regression coefficient, it looked like a circle. But in this case, because these are just absolute values, it's gonna basically look like a diamond. For example, when p equals to 2, it is actually modulus of beta 1 plus modulus of beta 2, which in a two-dimensional case is basically just a diamond here. So now this diamond basically has this sharp corner sticking out. The circle was quite an uniform thing, right? But diamond is not, doesn't look really uniform. It's rough in the sense that it has some corners sticking out. So for example, if you're walking randomly, maybe randomly walking towards your door, and your door has a furniture maybe just beside it which has a corner sticking out, so you'll probably mostly hit the corner of the furniture, and it will hurt you. Any which ways, the concern that I am talking about, that if something is sticking out, the probability is high that you are gonna go hit that portion. And the same thing happens here. The residual sum of squares, this particular contours are trying to reach the constraint, and then there are corners sticking out, so possibly they are going to hit at the corners. So what's the implication of hitting the corners rather than the edges here? So now, for example, obviously here was the least square solution, and now the solution comes back to this place, which means that the value of beta 2 has shrunk from this value to this value, which is a good thing because we are trying to handle multicollinearity by basically controlling the values of the regression coefficients. But the other implication is because here it is hitting it on the y-axis, which means that beta 1 is exactly equals to 0. So lasso is not only just shrinking coefficients, but it is actually eliminating the other regression coefficients entirely, which is why lasso is actually great for models with many predictors because it helps us focus only on the most important one. So it is handling multicollinearity, but it is also helping us with variable selection. So in summary, while both Ridge and lasso regression help prevent multicollinearity, lasso has the added benefit of feature selection or variable selection. So why is this necessary? Let's look at the next slide. So what happens in high dimensional settings, as in when there are more predictors than the number of observations in your sample size, is that traditional least squares or traditional regression faces the challenge of overfitting. So what's overfitting? When too many predictors lead to a model that fits the noise in the data and not the underlying pattern. So when you are dealing with high dimensional data, just minimizing the residual sum of square doesn't work. The model gets too sensitive to random noise in the data, which basically leads you to this overfitting issue. And that's where regularization helps. So techniques like lasso, they add a penalty on the coefficient, which helps control overfitting, and it automatically selects the most important variables. Here's an example of how lasso affects the coefficients in regression. So the bar chart on the left here shows the coefficients before applying lasso, where every feature has some influence. But after applying lasso, you can see as shown on the right that many coefficients are reduced to exactly 0. So this sparsity is what makes lasso powerful. It not only provides a predictive model, but also identifies the most important predictors, making it ideal for high dimensional data where many variables might be irrelevant. But this whole thing actually comes at a cost. So by shrinking the coefficients towards 0, lasso is actually underestimating their true values. So certain coefficients which are actually significantly large, even they are shrunk towards 0. So while the model becomes easier to interpret and then less prone to overfitting, it is important to understand this trade-off when using this kind of regularization technique. So this is what we call bias due to regularization. So let's try to first understand what is bias and what is variance. That these two terms are very fundamental to statistical concepts. So let's try to first understand them, and that will make it even clear how lasso is introducing bias into our model. So bias is basically the error that occurs when a model makes incorrect assumptions about the data. So imagine you are trying to predict something using a very simple model. For example, maybe you're trying to use a straight line to predict the house prices based on one feature like square footage. Now, the simple model might miss important patterns in the data like the effect of location or the number of bedrooms. So this results in systematic errors. So high bias basically leads to underfitting, meaning the model doesn't capture the complexities of the data and therefore performs poorly on both the training data and any new data. On the other hand, variance refers to the model's sensitivity to fluctuations in your training data. So think of a model that's highly flexible, like maybe a decision tree that can split data at every possible point. So if the tree is too complex, it might perfectly fit the training data, even capturing the noise or the outliers. And this results in overfitting, where the model performs really well on the training set, but struggles with any new or unseen data. So the high variance is due to the model being too complex and not generalizing well to new examples. So as you can clearly see from the definition of bias and variance that there's a crucial trade-off between them. If you try to reduce the bias by making the model more complex, you often increase the variance and vice versa. So the challenge is to find a balance. So to find a balance in the sense that a model that is neither too simplistic so that it does not have a high bias, nor too complex so that it does not have a high variance either. So ideally, we would want a model that generalizes well, meaning that it performs well on both the training data and the new data. But in case of lasso regression, the bigger villain is the bias, because lasso, what it did was, in order to take care of the variance, it inflated the bias too much. And now we need to hit a middle ground. So what's the plan? The idea is to correct the bias of the lasso estimator. How? So let's take a single regression coefficient, for example. So how do we do it is like we take this individual lasso estimate and basically just add a correction term which measures how much this lasso estimator is off from the truth, as in how much this beta j hat is off from the truth beta j, and then adjusts for it. So why does the bias correction term looks like this? So necessarily we want to get back the information that we lost. And what type of quantity gives that kind of information? It's the residuals, right? If you can recall what we talked about when we talked about the residuals. So we know that residuals is kind of information that it holds what your model cannot explain or what your model took away from you. So this quantity here, this y minus xi transpose beta hat, this quantity is basically, if you look at it closely, these are the residuals from your lasso fit, right? So the idea is to use these residuals to re-inject what lasso might have removed. And this u hat is just a correction term which projects this bias correction in the direction of beta j hat. Now that we have addressed the bias in our estimators, let's talk about how to quantify the uncertainty that remains in our estimates. So even after debiasing, there will still be some level of uncertainty, mainly due to the residual noise, the random fluctuations in the data that we cannot fully account for. So how do we capture and communicate with this uncertainty? We use something called confidence intervals. So a confidence interval, it quantifies the uncertainty around our estimates by providing a range of plausible values for the truth, for the true parameter. This helps us understand the precision and the reliability of our estimates. So we should not be done once we are like, okay, we have to best case a truth. So this is a methodology that we follow, and this is the best guess that we can have for the true parameter. We should also be able to say how confident are we about the estimate that we provided, and that is what confidence interval gives us. It's giving us basically a range of values that with a high probability or with a high confidence we can say that this range of values that is centered around our point estimate will be containing the truth. Now, the general formula for our confidence interval will look like this. So here's what's going on. This beta j hat here is actually our de-biased estimator corresponding to the jth predictor. So actually I should have written here beta j tilde if I basically follow the notation here. Beta j hat was the lasso estimator. We did a kind of a bias correction and then we got an estimator beta j tilde. So this is basically beta j tilde, and this SE is basically just the stochastic error which captures the variability of our estimator. And then this CV is what we call a critical value. So this value in layman terms, I can say that it basically stretches the range of the estimate to ensure that it captures most of the variability in our data. Now, why does this whole thing matter? Why will you even bother about confidence intervals? Because confidence intervals provide us with the measure of the precision of our estimate. So if we repeat the same process many times, the confidence interval gives us a range where we expect the true value to lie with a certain level of confidence. For example, a 95% confidence interval means that if we repeated this estimation process 100 times, 95 of these intervals would contain the true parameter value. In practice, confidence intervals are essential for understanding how reliable our findings are, and they tell us not just the point estimate, but how much uncertainty we have around it. I hope by now the methodology is clear, even if the theory and the minute details are not. Now you at least know how in a high dimensional problem you can propose an estimator. If not, the good news is you have a package function who does it for you. So we have designed an R package, SIHR, which is basically short form for statistical inference in high dimensional regression. And hopefully tomorrow you can have like a tutorial on how to use the R package itself, or basically in the R interface. But I will just introduce to you the function that is most relevant to today's talk. So this packet function has many other functions in it, but the most relevant, as I mentioned, will be the LF function. The LF stands for linear functional. And as the name suggests, it basically deals with the uncertainty quantification for functions of this form. So beta, you know what beta is. An extra is some given kind of a vector, and LF will be handling the inference, or I shouldn't be using the term inference. LF is basically handling the uncertainty quantification, like estimating, like it gives you the point estimate, it gives you the confidence interval and all kind of stuff for this type of a quantity for your high dimensional data. You can, so I'll just verbally tell you what all you need to supply to this function in order to get proper results. All you need to give LF is basically the X matrix, which is the matrix of your independent variables. You need to give it your Y vector, which is the vector for your dependent variable. Then you need to supply it with the vector X2, star, and then you need to tell it what kind of a model you are using. By that I mean whether your y is a continuous one or your y is a binary one, like is it like a 0 1 classification problem, or is it like a continuous variable, as in your y can take any kind of a decimal point, decimal values as well, or your y can be a count outcome, which means like y takes discrete values, but like it's not just binary, it's like a multi-class classification problem. You just need to mention LF, that what kind of y you are working with, what kind of a model do you have, and as far as you can specify all of these necessary arguments, the LF is going to give you the point estimate, it's going to give you the confidence interval. It actually helps in decision making as well, but I'm not going into that aspect. But if you want to explore this package function more, you are free to do that on this particular link. It is up on the CRAN, which is basically the R portal, and slowly and steadily the package is becoming popular, around 13,000 downloads so far. I would encourage people even from engineering background to give it a try, because you do not need to know all kinds of theory and minute details, but this function can basically blindly give you some results, and that can help you with your analysis. And now that you have listened to this talk, maybe you also have an introduction on how this package works. This package basically just employs the bias correction idea that I was talking about. Now I'll show how we can use the LF function to tackle a motif regression problem. So what's a motif regression problem? So this involves predicting transcription factor binding sites, or TFBS in short, also known as motifs in DNA sequences. So you can think of these as the landing spots on DNA where proteins latch on to control which genes get switched on or off. So these sites are like the on-off buttons for gene activity, and finding them is crucial for understanding how cells function. So using the LF function, we are trying to pinpoint the spots based on the patterns in the DNA sequence. It's like cracking the code that controls the genome. So the data set consists of an univariate response variable Y, which measures the binding intensity of the transcription factor on a coarse DNA segments. Then we have this data for around 2,500 genes. And moreover, for each of the N genes, a score describing the abundance of occurrence is available for 666 candidate motifs. Now we apply the package function LF, and we obtain 95% confidence intervals for all the 666 regression coefficients. And the constructed confidence intervals are illustrated in this figure. Now, among the 666 confidence intervals, 25 you can count later, maybe that there are 25 that are marked in red, and as you can see they lie completely above 0, suggesting a positive relationship between the motif and the binding intensity. Conversely, there are 23 of the confidence intervals which are highlighted in blue, and they are lying completely below 0, indicating that the corresponding motif has a negative impact on the binding intensity of the transcription factor. So overall, these results demonstrate that 48 motifs out of the total have a statistically significant influence on gene expression, and I think that offers quite a valuable insight into the regulatory mechanisms involved. Now, I feel we have talked enough about high dimensional inference for a single day. I'm going to talk about a type of a different but a related problem. It's a quite an interesting problem. Now people are getting in, more and more people are getting interested for this kind of problem. This is even a bit new to statistics as well. So I thought it would be a proper opportunity to introduce this kind of concept to the engineering people as well. So far we have been talking about conditional distribution of y given x, right? As in, given some feature x, how is our response behaving? This is what we call association, right? Trying to understand how X and Y are related, right? But a more important question can be, does an exposure, say A, cause Y? And this is not the same as association. For example, think of a drug trial. If you want to test if a medication works, what do? You give it to a group of people and you don't give to another group of people, and you observe the outcome, say heart attack rates, and you observe that from the true groups, the heart attack rates are different. Say the rate was smaller in the treatment group, that is the group that you treated with the medication, compared to the untreated group. What can you conclude from this observation? You can definitely conclude that, yeah, the heart attack rate is associated with the drug, but is this enough evidence to say that the treatment reduced the heart attack rate? If both the groups are very similar, maybe in age, health, and habits, then they are comparable and everything is still fine. But what if one group is older and sicker? You now can't tell if the drug worked or if the healthier group just had better outcomes anyway. So we need a better way, or altogether a better understanding of this kind of a causal problem. So how do I mathematically quantify this? So here comes the potential outcome framework. So each individual in your study framework has two potential outcomes. One is Y1, which is the outcome if the corresponding individual is treated, and then Y0, which is the outcome if the corresponding individual is untreated. Then the causal effect for the particular individual is the difference between these two. But the problem is, for a particular individual, we can only observe one of these outcomes. Why? Because either the individual is treated or it is untreated. You cannot observe both the quantities simultaneously, because if the individual is treated, then that rules out the possibility to observe Y0 and vice versa. Instead, what can we observe? If we are provided with a data set where some individuals are treated and some are not, we can measure the association between the treatment and the outcome, as I just mentioned during the last slide. So we can measure if the treatment and the outcome are related or not. So are there any condition under which we can say that association can help us get to causation? The short answer is yes, but we need to rely on certain assumptions. Now let's try to break down those assumptions. The first one is ignorability or exchangeability, which basically means that the two groups or scenarios that you are working with, they should be comparable, so that other than from the treatment or the exposure, everything else is effectively the same. Because if this is true, then any difference that we see between the groups, any difference in the outcome that we see between the groups can be attributed to the treatment itself. So exchangeability is like making sure you are comparing apples to apples. So if we can observe and condition on all such common factors that affect both the treatment and the outcome, then the change in the outcome can be attributed to the treatment. So that's quite an intuitive assumption, right? The next is the positivity assumption, which says that everyone has a positive chance of receiving the treatment. What can be a possible violation? For example, if a physician knows that the treatment is harmful for a patient, he or she won't ever advise the patient to take the medicine, right? But then that is a violation of the assumption, since the probability or the chance of receiving the treatment for that particular patient is exactly zero, and that's not allowed by this assumption. And thirdly comes the consistency assumption, which means that there's no ambiguity or variation in what the treatment means. Now, under these assumptions, we can prove that the causal effect estimation basically boils down to an associational problem, to a regression problem. Now, what happens if some common causes are unobserved so that you cannot even control for it? For example, let's say we are evaluating the effect of pollution on health. Now, factors like lifestyle habits, such as exercise or diet, they may play a critical role, but they are often unobserved. Now, without accounting for these hidden influences, any conclusions about pollution's impact will be misleading. So this is actually a major issue in the real world studies and is where more advanced approaches come into play. Now, one such avenue is what we call a proximal causal inference. So this particular avenue of work, instead of requiring the direct measurement of U, so U here is basically the unmeasured influence. So this particular avenue of work, it uses proxy variables. So what's a proxy variable? So basically they are saying that even though I don't observe this important variable U, I measure some variables Z and W, which are very strongly related to U, but not exactly U. So it specifically needs two types of proxies. The first type is what we call treatment confounding proxies, or basically I denote them as Z here. So these are variables related to the confounder U, but not directly to the outcome Y. Then comes the outcome confounding proxies, we denote it by W. They are related to you, obviously, because they are proxies for you, but not directly to the treatment A. Now, why such assumptions like Z not affecting Y and W not affecting the treatment? This is simply to disentangle the effect of this unmeasured U on A and Y. And this is the only requirement that proximal causal framework has. So as long as you can find proxies that are sufficiently rich in a way that they do not interact with each other, proximal causal framework will leverage these proxies and adjust for the unmeasured U. So now just a bit more details on how proximal causal methodology works. So mathematically, this is how basically the outcome model is given as, and you will say that this is exactly the same as the regression problem we were looking at, right? But the issue here is like U is unknown to us. You are not actually observing U, so you cannot really go on with this kind of a regression framework. So just repeating myself, what are these variables here? Y is the outcome we want to explain. A is the treatment or the exposure that we are interested in. So basically we are interested in estimating this vector beta, which is unknown to us, because this is the one which is going to tell us how the treatment A is affecting our Y. Now U is the hidden confounder, which is unobserved, but it influences both A and Y. So without accounting for U, I cannot make any conclusion about the effect of A on Y. And then epsilon is basically just a random noise. So ignoring U is not an option because U is affecting both A and Y that we have already accepted. So to address this, we use this proxy variable W, which is related to U but is noisy. So in other words, W carries some information about the hidden confounder U, but it's not a perfect representation. So the goal is to extract the part of W that truly reflects U while filtering out the noise. And this extracted part will act as a substitute for the hidden variable U in our analysis. So what do we do to isolate the relevant part of W? We make use of the observed variables, which are the treatment A. And if you can remember, there was another proxy variable Z, which is also related to U. So we estimate W hat which represents the part of W that can be explained by the observed variables A and Z. This tape essentially captures the component of W that correlates with U, allowing us to approximate this hidden confounder U. So using W hat, we rewrite this outcome model here. So here, A beta still remains the same. They have the same interpretation. Now this W hat times gamma, it accounts for the effect of the hidden confounder as approximated by this W hat. And this epsilon W is the residual error after incorporating W hat in place of U. So once we have reformulated this model, we can simply use ordinary least squares or, if required, lasso or any kind of regression techniques to estimate beta, which is the causal effect of A on Y. Now, the key insight here is that by including W hat in the model, we effectively control for the hidden confounder U, enabling us to obtain an unbiased estimate of beta. So in summary, this process ensures that the unmeasured confounder U does not bias our causal estimate. Instead, we leverage proxy variables like W and Z to approximate U, reformulate the outcome model, and then use standard estimation techniques to cover the causal effect. So to wrap up, in the second part of the talk, we learned that mere association does not necessarily mean causation. To make use of the regression models, you need to make sure that you are taking into account all common causes that can affect both your treatment and the outcome. And in case you miss out on something, or you are aware that you are missing out on something whose proxies are available, then you measure those proxies and leverage them to get an estimate of your causal effect. With that, I think I'm gonna conclude my long lecture, a long talk on regression analysis and the new concept of causal inference as well. And I'm gonna maybe open the floor for possible questions or queries or doubts.
Adi. Thank you, Dr. Rakshit. Any question from the audience? We are really thankful that, considering our time crunch, you have managed your lecture in a time efficient manner, but you have given a very lucid presentation. But as most of us are just first time, maybe because I know there are many first time learners of statistics related to machine learning and AI, so obviously they need much more time to understand the concepts you have just highlighted. And our coordinator has already started to share the video lectures, and I believe that after going through your lecture they will be more open to communicate their queries to you via mail, though if they are not ready here to ask the question, so they should be given sufficient time to understand the topics. So I should be sharing your video lecture with them. So it's really, really a great honor for all of us to have here for this lucid and nice presentation from you. And specifically, as this is a new field, obviously not theoretically, but obviously the connection between stats with all the technologies we are discussing. And most of us are here from the engineering background. So we are really grateful for your thoughtful presentation, the way you have thought of our background and have prepared the presentation like that. So thank you very much. So I would like to request Anuradhadi, if you are here.
Yes, Pratyusha.
Yes, I mean, as you were taking the screenshots as per the
Yes,
FTP
yes.
formalities, so on behalf of Anuradhadi, I am requesting the participants to kindly switch on your cameras to help her to capture the screenshots.
হ্যাঁ, অন করো তাড়াতাড়ি। আইতাছি না, সবাই অন হয়ে গেছে।
Thank you, dear participants.
আচ্ছা।
Thank you for your patience. And I must say, Dr. Prabhisha, thank you so much for your informative session.
আহ,
It is our greatest
বইটা বন্ধ করে
gratitude
দিচ্ছি।
that you have given us so insightful presentation on lasso regression, confidence in interval, precision estimates, multi-functions as well with high dimensional data. And also you demonstrated that in today's world, the statistics and our machine learning just goes hand in hand, and also, make us
রিপ্লাই দেন।
understand the importance of debiasing in machine learning models. So always we thought of, always we thought of applying the statistical analysis while we are estimating the performance of our classifier and everything. Pratusha might may be agree with me. So your presentation not only showcased the cutting edge research with proximal causal inference and all the statistical analysis, but also underscored the real world applications and benefits of these techniques. So I thank you once again for truly engaging and impactful session, Dr. Prabhisha. Thank you very, very much. So thank you, dear participants. So I would like to wish all the good night. And today tonight is the last, but the before the I can say the last, but one such day, that is the fifth day of the AICT Auto Online FTP. And on the last day, that is on the Saturday tomorrow, I would like to remind you that it is a new timing. Don't forget, we have 3 sessions tomorrow from starting from 2 p.m. One we have 2 p.m. to 3:30. Then we have the next session from 3:30 p.m. to 5 p.m. and then 5 p.m. to 6:30 p.m. So we have 3 sessions with 3 eminent speakers with 3 different backgrounds, which are really going to be very, very exciting for us. And after 6:30 p.m., when we will finish with the third resource person tomorrow, then we will have a small valedictory session from 6:30 p.m. to 7 p.m. And then you will have an online test from 7 p.m. to 8 p.m. So all the links will be provided in the chat box as well as in your mail as well as in your WhatsApp group. So I request you, it is my humble request to you to just go through the mailbox. If you cannot find the mail in your normal inbox, I am constantly, requesting you, all of you, to just search the mail in the spam folder as well, because every time whatever we are sending the information, we are sending everywhere. So today also I have shared some video lectures till yesterday what we have already processed, we have already shared. Yeah, you will be also given, today's lecture or tonight's lecture, by tomorrow morning or tomorrow noon. I'm going to, I will try my level best to provide you as well. And some, request has already been sent to the resource person to kindly send the ppt or the paper from where actually they have prepared the ppt or they have shared the knowledge. So once we will be getting all those resources, we will be providing you through WhatsApp or through email. So please be alert, because we are going to provide you all the resource materials, however and whichever way possibly we are actually in the process of collecting everything for you. So on this note, I again thank all of you to participate in this ATAL FDP, and also wish you good night. So very good night, and let's meet tomorrow on the final day at 2 p.m. Thank you so much.
Thank you, ma'am.